and thanks for having me out here. It's an honor to be giving the first JINA CEE seminar for your semester. I'm going to be talking today about constraining the dense matter equation of state using neutron star mergers. Specifically, I'm going to be telling you about some of the things we've learned from the first detection of gravitational waves from the neutron star merger, and then hopefully what we might be able to learn from future detection events. So to start with a little bit of motivation, this audience probably doesn't need, but why we should care about neutron stars in general, either from an astrophysical perspective or from a nuclear equation of state perspective. So as you probably know, neutron stars are one of the two possible outcomes for the deaths of massive stars. And so for those of us who care about studying the late stages of stellar evolution or the explosion mechanism behind a supernova, neutron stars offer a natural fossil remnant of those processes. Neutron stars also continue to be one of the best test beds for general relativity that we know of. They're also now the confirmed site of gravitational waves, at least from neutron star mergers. There's been rumors of a potential neutron star black hole merger that was recently potentially detected. And in the future, we might be able to detect gravitational waves from isolated neutron stars as well. And from that first detection of gravitational waves from a neutron star merger, it was also confirmed that these mergers were the engines driving gamma ray bursts, which are one of the most energetic phenomena observed anywhere in the universe, and also the associated kilonovae, which are powered by the radioactive decay of heavy elements. We now had the link connecting these electromagnetic phenomena following the detection of those gravitational waves. And then the perspective that I'm going to kind of focus on in this talk, that's perhaps of most interest to this audience, is that neutron stars contain the densest matter found anywhere in the universe. And so they provide a natural way of probing the dense matter equation of state. So what do I mean by dense matter? This is the cartoon picture, right? But we all know physics 101 tells us atoms are mostly empty space with some nucleus surrounded by a cloud of electrons. And as we start to compress to higher densities, of course, it becomes energetically favorable for the electrons and protons to combine, and you end up with very neutron-rich matter where all that empty space has been squeezed out. As you start compressing to even higher densities, though, the picture is less clear, and it's not necessarily what happens to matter at the ultra-high densities. So I have one depiction here, which is the prediction that the individual boundaries surrounding these nuclei dissolve at the highest densities, and you get deconfined quark matter. But of course, that should probably have a little bit of a question mark over because we don't know what the end state is. There are lots of predictions. And of course, at those ultra high densities, the energies of the particles are so high that you can get emergence of new exotic forms of matter, whether those are hyperonic matter or say pion or kaon condensates and so on. So more quantitatively, right, low densities, the kind of heavy metals on Earth have densities on the order of 10 grams per cubic centimeter. The matter I'm talking about in the cores of neutron stars are 14 orders of magnitude denser, roughly 10 to the 15 grams per cubic centimeter, or roughly 8 to maybe 10 times the nuclear saturation density. So we can also sort of orient ourselves using just a cross-section of the QCD phase diagram where I'm showing you sort of a high density cross-section, and I'm choosing to display temperature as a function of the neutron excess just to make it clear the part of parameter space we're in. And so, right, a lot of the studies in the nuclear community focus on the left side of this plot with fairly symmetric matter, either studies of finite temperature nuclei that are relatively cold, or the nuclear experiments like are done here, where you have fairly symmetric matter, so fairly equal numbers of protons and neutrons at high temperatures. And neutron stars, of course, fall in the other corner of this phase diagram where you have almost pure neutron matter at very, very low temperatures. And so if we care about pinning down the equation of state in this part of the parameter space, neutron stars offer us a natural probe. So this is where I'm going to start talking about this gravitational wave event. You all have probably heard about it many times over by now, but we just celebrated the second birthday of this event. But on August 17th, 2017, the LIGO-Virgo collaboration, which is this interferometric experiment to measure gravitational waves, triggered on an event that they soon confirmed to be a neutron star merger event. They announced this event, and over 70 different observatories around the Earth and in space pointed their telescopes and scanned the sky to identify the electromagnetic counterpart, which was then identified across the electromagnetic spectrum. You can see here the actual signal in the gravitational waves. This is a spectrogram showing the frequency evolution as the two stars spiral inwards until they ultimately coalesce. It's clearly visible in the two LIGO bands. It was not seen in the Virgo band. I just want to point out that these 30 seconds in which the neutron stars were in the LIGO band until they ultimately coalesced corresponded to the final 3,000 orbits for these two neutron stars before they combined. And so it's by fitting that data that the LEGO-Virgo collaboration was able to extract a number of properties for the two neutron stars in the system. So there's a lot here. I want to focus on just two of the properties in particular. The first is the masses of the two neutron stars. On their own, these are two roughly 1.4 solar mass neutron stars, which is not extraordinary. That's sort of the canonical mass that you might expect for a neutron star. But you'll notice that the individual component masses are only very broadly constrained. It turns out that the two component masses in the system are very highly correlated. Instead, the parameter that is easier to extract and is more precisely measured is the so-called chirp mass, which is just an effective binary mass for the system. And for this event, I want to point out specifically that the chirp mass is a precision measurement. It's measured to within 1/1000th of a solar mass, which is an accuracy that's sort of unmatched in typical astronomical type observations, or at least rare. The other parameter that I want to point out that was particularly exciting for the neutron star equation of state community is the measurement of the tidal deformability, because this was the first ever real probe we have of the quadrupolar moment of the mass distribution from a neutron star. So the tidal deformability is just defined as the quadrupolar response of an object to the tidal potential of its binary companion. So if you imagine you have a neutron star whose stellar structure is determined by the pressure profile within the star. If you imagine having a relatively large pressure at every given density, that large pressure is going to move individual mass elements far away from the center of gravity. So you end up with a very puffy extended mass distribution, which corresponds to a large radius star. And that star, because it has such an extended mass distribution, is easier to tidally deform in the same gravitational well compared to a more compact star that has a smaller radius and a more compact mass distribution. Right, and so you can see this in the little GIF that's been playing here, that for two stars that are of the same mass and at the same separation, the larger, puffier neutron star is easier to tidally deform compared to the smaller compact star that remains relatively unchanged. We can write down a relatively simple expression to describe the tidal deformability of one of these stars, where we call it, the parameter is lambda, scales like effectively the mass over radius to the -5th power, which is exactly what I was just describing to you. Large radii means large tidal deformability, which means it's easy to disrupt. The reason we can write this down this quantity in such a simple expression, even though neutron stars are inherently very complex objects, is because we're hiding all of the detailed microphysics with this parameter K2. And so that's the parameter that depends a little more sensitively on the equation of state. It turns out that for hadronic equations of state, it spans sort of a narrow range between about 0.05 and 0.15, which is why it's typically sort of isolated. But that's hiding the stronger equation of state dependence for the parameter. The reason we can measure this is because when you have a tidal bulge in a star, it makes your mass distribution asymmetric. And so if you have an asymmetric extended mass distribution moving around and changing your space-time, that's going to produce an additional gravitational wave signature compared to if you just had 2-point particles orbiting each other. And so you can see this is just a model waveform where the two polarizations of the gravitational waves and the dashed lines are the model that you'd expect if you just had 2-point particles in spiraling and then ultimately coalescing, which is when the signal starts to die off quickly. And then the solid line is the model where you're including the effects of having this asymmetric mass distribution, this tidal bulge in your star. And you can see what it produces is a slight phase shift in the waveforms when you allow for these tidal effects in your waveform model. And so it turns out that the size of that phase offset is related to the strength of this tidal deformability parameter. And so you can extract it by doing a detailed waveform model analysis. But it turns out that just like it's very difficult to disentangle the two component masses of star 1 and star 2 in the system, it's also very difficult to disentangle the tidal deformabilities of the two stars. Instead, what you measure, what is the parameter that is most cleanly extracted from that waveform fit, is called the effective tidal deformability of the binary system, which we give the special name lambda tilde, which is just a sort of messy mass-weighted averaging of the tidal deformabilities of the two stars. And so the expectation is that this parameter lambda tilde is going to measure some mass-weighted averaging of the stellar compactness, how much mass you have in a given radius, that has some additional dependence on the equation of state through that K2 factor. From GW170817, the LIGO-Virgo collaboration released full posteriors on lambda tilde, which are shown here as the blue kind of solid curves. And the first thing to notice is that lambda tilde, which can range anywhere theoretically from 0, which is the limit for a black hole that you expect not to be perturbed by companion's gravity, all the way up to values of a few thousand, which aren't even shown here for a very extended mass distribution, that this single event is already telling us that the tidal deformability for the star is relatively small, peaks at values of around 200, perhaps telling us that these stars are relatively compact. You can also see shown here, the vertical lines are the predictions of various theoretical equations of state. So we can also do sort of a case-by-case comparison to say that some classes of equations of state are less likely from this data. But when this tidal deformability parameter was first announced, it wasn't obvious that we were going to be able to do a lot more than this. That is, that we were going to be able to do much more than a qualitative hand-wavy argument saying this is meaning that stars are compact, or this case-by-case comparison with particular predictions. Which is why when we started doing our follow-up analysis of GW170817, we were surprised to discover some evidence of a new universal relationship seeming to emerge from this data. And specifically what we find is that when you fix the chirp mass from a gravitational wave event, which remember is this precision measured quantity, it turns out that lambda tilde becomes insensitive to what you choose for how you divide up the mass between the two stars. So I can vary the component masses however I want, and as long as they give the same chirp mass, you get the same effective tidal deformability of the binary system. And instead, what you see is very clean separations in the binary tidal deformability for neutron stars that differ in radii by, a kilometer or so. This becomes a little bit more obvious if I switch my axes. So I'm now plotting the binary tidal deformability as a function of the radius. And on this plot, each of these clusters of points correspond to the predictions of a different theoretical equation of state. Within each cluster of points, I'm varying what I'm choosing for the two component masses, and you can see that, right, it's insensitive to those choices. But that all of these theoretical equations of state seem to be following this same trend line. And in our paper where we describe this, we kind of show the origin of this effect using a quasi-Newtonian expansion, which I bring up just to point out that this purple band is not a trend line, that's not a fit, that is actually the analytic prediction that we come up with our paper, and the width of that corresponds to the uncertainty in the masses from the gravitational wave event. So this is a very precise sort of one-to-one mapping that this allows us to do between this binary tidal parameter and the neutron star radius. And so it's really powerful because now we can take the constraints on lambda tilde from the gravitational wave event and directly convert that to constraints on the radius and say that the neutron star radius must be, say, less than about 12 kilometers or so. Now, why is it so powerful to want to convert gravitational waves to neutron star radii? Well, one of the main thrusts of the neutron star equation of state community for the last decade or so has been to observationally constrain the neutron star radius using X-ray observations. So these X-ray observations come from neutron stars and low mass X-ray binaries, typically, where you have a stellar mass companion, a stellar type companion, accreting some matter onto the surface of the neutron star, and the measurements can either be made during quiescence, so when the accretion temporarily stops or slows, and you can measure the X-ray properties of the surface, or during the so-called thermonuclear bursting state, when enough accreted matter accumulates onto the surface of the neutron star that you actually undergo a thermonuclear ignition that can actually lift the surface of the neutron star temporarily. And from these we can model, extract the properties of the apparent radius. And so you'll notice, so we have the community has X-ray measurements for about 15 or so different sources. This is a summary plot of some of the most recent ones. And you'll notice that, right, any one of these individual measurements still has pretty large uncertainties, but they're overlapping. And so we can combine these in a statistical sense and find, when you do that, you find that the neutron star radius is between about 10 and 11 kilometers, depending on exactly what you put into those modeling, into your models. And so what this means is that with our new relationship that lets us do this one-to-one mapping between the binary tidal parameter and the neutron star radius, we can now do a direct comparison of the neutron star radius as measured from the gravitational waves, which are shown in the dashed line, from the X-ray data, which are shown in the dashed line here, and from the gravitational waves, which are shown with the colorful lines. And so these two independent methods for measuring the neutron star radius, right? One comes from X-ray photons and one comes from gravitational waves. They suffer none of the same modeling uncertainties or systematic biases, are already pointing towards common values of the neutron star radius, which was a pretty exciting result to see right off the bat. It's still a fairly large spread for the gravitational wave inference. We are still only working with a single event. As we start to detect more and more of these, we can build up a statistical ensemble and hopefully start to shrink those error bars. And then it'll be really interesting to see if we can get competitive constraints with the X-ray data and really start to pin down the neutron star more rigorously, or if there's any tension, and that can help us then potentially pin down systematics in either analysis method. So one important caveat that I need to mention is that those constraints on the neutron star radius made, depending on who you ask, a potentially strong assumption about the equation of state, which is that we assume effectively no substructure in the equation of state, so no phase transitions at high densities. And so if you believe that the equation of state really is nuclear to high densities, then those radius constraints are fairly robust. But if there is a phase transition, say to quark matter at high densities, then this is not the approach you want to use. And there have been a few papers that have shown that, and basically what they have found is that if there's a phase transition in your equation of state, then lambda tilde now starts to depend more strongly on how you divide up the mass for the two stars. So it depends more strongly on the component masses, and so this clean one-to-one mapping breaks down. And in particular, what it means is that if you measured two neutron star mergers with identical chirp masses, you could, in theory, measure two different tidal deformabilities from the two systems. I mean, so this is a caveat, right? Because it means, you know, there's some qualifications to the constraints I showed you on the neutron star radius. But this feature, I think, is also a potentially powerful diagnostic tool in its own right. Because what this means is that if we ever get to a point where we have a large sample of neutron star mergers, and you can actually identify two stars with similar chirp masses, if you can tease out two different tidal deformabilities, this will be a smoking gun indicator of the fact that there's a phase transition in the equation of state. So we have now a constraint on the neutron star stellar structure using the radius as a proxy. But we can also ask ourselves if there's a way to more directly constrain fundamental nuclear parameters. So in particular, I'm going to mention the nuclear symmetry energy. This is just a cartoon version to remind you all, right, that the symmetry energy is defined as the difference in energy between symmetric matter, which has equal numbers of protons and neutrons, and the less energetically favorable composition of pure neutron matter. And of course, this difference in energy depends on how closely packed the particles are for either composition, and so it's a function of the density as well. And one of the common ways that people tend to write down this density dependence is with a simple series expansion, where they're expanding about the nuclear saturation density and going to higher densities. And I bring this up just to point out that the coefficients of each of these terms are the subject, of course, of a lot of experimental constraints that many people in this room have worked on in the past. In particular, the first two parameters, S0, which is the value of the symmetry energy at the nuclear saturation density, and L, which is basically a slope-like parameter controlling the leading order density dependence of the symmetry energy, have been the subject of a lot of constraints. On the left is a plot from one of Betty's 2009 papers, and on the right is a review paper by Latimer and Lim. You can see that these different experimental constraints, whether they're from the heavy ion collisions, fitting nuclear masses, measuring the neutron skin thickness, and so on, each of these different types of constraints limits the allowed range of values for S and L. And when you combine these, they seem to point towards allowed values of L between about 40 and 60 MeV, depending on which of the analyses you include in that combination. I'm focusing in particular on the parameter L, because there has been a sort of long-standing knowledge in this field for probably 20 or so years that this slope parameter of the symmetry energy L tends to correlate very strongly with the neutron star radius. And this is just a recent paper showing this, where you can see that smaller values of L tend to correlate with smaller neutron star radii, and larger values of L correlate with larger neutron star radii. And so you might see where I'm going with this, but we just saw that there is this strong correlation between the binary tidal deformability parameter and the neutron star radius. And now I'm telling you there's this relationship between the slope of the symmetry energy and the neutron star radius. So it might be natural to ask ourselves, can we use the gravitational waves to constrain this L parameter? The problem is that this is a multi-dimensional problem, right? So if you want to include all of these coefficients, we're talking about 4 parameters to orders that are typically included, right? You could include it to infinite parameters, but typically people use at least the first 4 coefficients when writing down the symmetry energy. And this is just the parameterization for this symmetry energy, which is the penalty for having unequal numbers of protons and neutrons. If you want to describe the total energy of your neutron star, you also need to add in the symmetric matter energy, which adds at least an additional 2 parameters, depending on what assumptions you make. So you have this, at minimum, 6-dimensional parameter space, and we expect one of these parameters to have a dominant role. So the question is, how can we show that in a clean way? And so what we have done to sort of simplify this problem and make some headway is to introduce what we consider to be a fairly physically motivated simplification, which is that we assume that the equation of state of dense matter has a simple expression so that it just follows a single power law density dependence just in the vicinities near the nuclear saturation density. So in particular, between 1 and 3 times the nuclear saturation density. Most realistic equations of state that are calculated don't have a lot of substructure at those relatively low densities from a neutron star perspective. And so it seems that perhaps making just this simple simplification in this limited density range is perhaps plausible. And by making that simplification, we're able to reduce our parameter space so that our equation of state effectively only depends on the slope that you assume across that narrow density range, and the value L, which is the parameter we're after. It also depends on S, but it makes a small difference, and so I'm not going to mention that for right now. And it turns out that for realistic choices of those nuclear coefficients, that this parameter gamma is also fairly narrowly constrained. So effectively, our equation of state depends primarily on this slope of the symmetry energy L. And so we can start to vary the parameter L and see what happens for our binary tidal deformability, and you get a similar one-to-one mapping with what we saw before. And you can now do the same sort of analysis where we can take the constraints on the binary tidal deformability and map those directly to constraints on the parameter L. And so these are the results that we find. So the thick blue line is our basically most likely constraint on L from GW170817. The 2 green bands are showing different sets of summary constraints that are based on some astrophysical measurements, some theoretical calculations, and also on the nuclear physics experiments. In particular, the lower boundaries of these are set, I believe, by the heavy ion collisions. And so, I mean, the constraints that we find from GW170817 are very broad. They are consistent with the results from the nuclear community. But you'll notice that the peak likelihood we find is closer to 20 MeV for L, which falls outside of the allowed range from the nuclear experiments. Now, theoretically, I think that is very hard to explain. Yes? We did not go below 0. It becomes hard to model with our simplification. The equation of state becomes unphysical if it's negative, just because we don't have other parameters that can correct for that. So you get a negative pressure. Yeah, good question. Right, so we're finding that these gravitational wave data, if you just go based on the gravitational wave data, are perhaps pointing to lower values of L than have previously been found. Now, this is a modest tension at best based on a single event. If this is confirmed in future detections, I think there are kind of 2 possible explanations. On the one hand, perhaps our simplification is introducing some bias in this analysis that is pushing us towards lower values of L. That's possible. We haven't been able to track down any such bias. If anything, our analysis is actually pushing us towards higher values of L, but perhaps there's some artifact from our modeling simplifications. The second, I think perhaps potentially more interesting interpretation, if this is confirmed, is perhaps that we're not quite yet comparing apples to apples in this comparison. So the gravitational wave data come from more neutron-rich matter than what is probed in the nuclear experiments, and typically colder. The early in spiral is still very cold when this parameter is set. And so perhaps there's some extrapolation uncertainties that need to be taken into account in order to do a true one-to-one comparison here. But like I said, it'll be interesting. We'll have to see if future gravitational wave events will help resolve this question. Yes?
I agree that the sensitivity of the gravitational waves is stronger for a single degree review than it is for symmetric matter equation state, but the symmetric matter still has some sensitivity there. Particularly if you change your K0 value, you can change your deformability. So what did you assume about the symmetric matter?
So when you make the simplification here, that we're requiring a single polytrope at saturation density, the only parameters that survive when you actually do the derivatives are L naught. So K0 is...
K0 is not even in the expression.
Right, so K0 is in the symmetric matter, right? That is a zeroth order or second order term?
Second order.
Second order term, right? And so at the saturation density, it disappears.
Yeah.
And so that's why this analysis requires you to assume this simple expression at the saturation density. And so then the only thing that's anchoring your equation of state, the only parameter that survives is L. And so it requires, right, that whatever is determined by L at the saturation extends and is valid for a limited range of densities we require up until 3 times the saturation density, but it's just, does that answer your question? Okay, yes. I know the Latimer and Lim paper does include the X-ray radius constraints. I think the Ortel paper does as well. But those aren't what's setting the lower limit. And I'm not, I guess here.
I'm just wondering if you only include the gravitational wave. I mean, in earlier slides, you had 10 to 11.
Yes. So that was also, I think the X-ray radii that they're including these analyses are probably closer to 12.5 kilometers, which would be slightly larger L than the gravitational waves are perhaps pointing to. Mm-hmm. Okay, so both of those constraints that we've now seen on the neutron star radius and on the nuclear symmetry energy both come from this global tidal deformability parameter for the binary system lambda tilde. There is a second way, though, that we can constrain the equation of state using the gravitational wave data, and that is instead of using this global macroscopic quantity to describe the matter effects, the tidal bulge in your waveform, you could alternatively write down a waveform model that depends instead directly on some equation of state function. And the way people do this is to use a parametric equation of state, often constructed of polytropic segments, so you just have these power law segments with density. And so you can write down a waveform model where all of the matter effects are directly connected to this equation of state, the parameters of your equation of state. Now, this is a lot more computationally expensive to fit for this. You have more parameters, and you have to actually decide what these parameters do to the global properties, which requires some integrations of the stellar structure. So those are the downsides to doing this more computationally expensive method of extracting equation of state constraints. But it is nice because then you can directly place Bayesian priors on each of these parameters. And if these are what you fundamentally want to extract, this is the more direct way to get at it. And so in their analysis of 170817, the LIGO collaboration did basically 2 independent analyses. One in which they describe all the matter effects using that global tidal deformability parameter, which is what we've seen so far. And then they did a second independent analysis where they were fitting directly for those equation of state parameters. And so these are the constraints that they found from the direct fitting of the equation of state parameters in this equation of state space, using one of those polytropic parametric equations of state, shown here in the green dashed bands. And just for comparison, I have also put as orange and blue bands sets of summary constraints that were previously basically the state-of-the-art constraints from the neutron star community. And so the orange and blue bands, which are hard to see, are the constraints that are derived using the X-ray observations of neutron stars, the observation of a 2 solar mass neutron star, and some nuclear priors as well, and then all combined with a Bayesian inference scheme to constrain the equation of state. And so you'll notice that the gravitational waves overlap almost identically with those radius constraints just from this one event so far. The other points I want to point out, there are some problems with doing these parametric inferences of the equation of state. They can miss substructure in your equation of state, and there are other sort of statistical issues with them. The 2 points are constraints on the equation of state from 170817 from an independent analysis outside of the LIGO-Virgo collaboration that use a non-parametric inference scheme with Gaussian processes. And so they are also finding consistent constraints with slightly different sets of priors. And so hopefully the statistical issues aren't the problem here, aren't the only reason we're seeing such good agreement here. But the other thing I should point out is that these different sets of constraints all have different uncertainties because it's just a summary plot, but already the LIGO-Virgo constraints just from this one event are already starting to be fairly competitive with the previous sets of constraints from X-ray radii. And so hopefully as we detect more and more of these events and start shrinking these uncertainties, we'll have potentially competitive constraints and get more stringent information on the equation of state. So for the last few minutes, last section of my talk, I want to switch gears a little bit to a topic I've been thinking a lot more about lately, and that I think this community will hopefully be going in with these, trying to understand future detections of gravitational waves. And that is to start thinking about how we can do a more robust treatment of the thermal physics. So all of the equation of state constraints that I have shown so far in this talk have been for the cold equation of state. So for isolated neutron stars, and even in the beginning stages of neutron star merger, the matter is effectively cold. The average energies of the particles are well below the Fermi energy, and so there's no significant thermal effects, and we just model the matter as basically 0 temperature. But in the very late stages of the neutron star merger, there can be significant shock heating that can raise the temperature of the system to some tens of MeV, potentially even 100 MeV, depending on what you assume for the 2 initial neutron stars. And so having that additional source of thermal pressure is going to affect many of the late stage observables that we might hope to detect from future gravitational wave events. So in particular, after the 2 neutron stars merge together, there's going to be some remnant object, either a massive neutron star that might survive for some short amount of time, or a black hole if it collapses promptly. But as that object relaxes to its equilibrium state, it effectively rings down, and during that ring down phase, it emits what are called post-merger gravitational wave frequencies, shown here, that are expected to be a very sensitive probe of the neutron star equation of state. Additionally, all of these the shock heating in the late stages of the merger will also potentially affect the electromagnetic counterpart. So perhaps how long that remnant can survive for, what its lifetime is, will be affected if you have more thermal support that can help it survive for longer. How much matter is ejected is going to affect both the strength and duration of the electromagnetic counterpart, and is also going to affect things like R process yields for how much matter is available to undergo the R process nucleosynthesis. And so if our goal is to be using these late stage observables to constrain the cold equation of state, we need a really good model to be able to disentangle the role of the thermal pressure from the cold pressure, because the thermal pressure is going to affect all of these observations. There are basically 2 ways that you can have such a good model. The first, and perhaps the ideal, is to have a fully self-consistent finite temperature equation of state that allows you to calculate the pressure at any density and temperature, and composition for that matter, in a self-consistent manner. There are some of these equations of state that exist in the literature. The problem is that they are relatively few in number, and they span a relatively narrow range of possible physics. So for people who really want to do a wide exploration of the possible underlying physics, they've kind of taken on an ad hoc approach, which is to divide the total pressure into the cold and thermal components. For the cold component, then, you can do kind of whatever you want. Just do simple, a parametric equation of state, some sort of power law, piecewise power law type cold equation of state. And then they tack on a simple model of the thermal pressure. And conventionally, traditionally, the way that this is done, for at least for many neutron star merger simulations, is when they model the thermal pressure, effectively the model is to consider the low density matter as just being dominated by your ultra-relativistic sea of leptons and protons, and rising to be the thermal pressure predicted for an ideal fluid at high densities. And this is nice because it's very computationally simple to implement, which is convenient for neutron star merger simulations, which are notoriously computationally expensive. And it gives you some first order approximation of the thermal effects. The problem is, of course, that at high densities, like you expect to find in the cores of neutron stars, your matter is not ideal, but it is strongly interacting. And so at very high densities, as this degeneracy sets in, some of the available free energy goes into those interactions between particles, and you see this characteristic dip in the thermal pressure at very high densities. And so this ideal fluid approximation can overestimate the actual thermal pressure for this degenerate matter by orders of magnitude at high densities. So, why not just write down what the thermal pressure is for degenerate matter? Well, in this framework I'm describing, we're doing a very agnostic treatment of the cold pressure. People are just assuming simple power laws. To write down the full thermal pressure for the degenerate regime, you need to have some knowledge of the interactions between the particles. And so that's why people have typically neglected that, because you just don't have that information when you're doing a parametric cold equation of state. So to sort of work around this problem, we have introduced a new framework that we think helps resolve this issue, which is we introduce an approximation of the Dirac effective mass. So this is the effective mass in a relativistic mean field theoretic sense. And we use this parameterization of the effective mass as a proxy for parametrizing the interactions between particles. And so we just take advantage of the asymptotic behavior of the effective mass, so that at very low densities, the effective mass just goes to the nucleon mass of the system, and that at high densities, it undergoes this sort of characteristic power law decay. And we find that basically a two-parameter model for parametrizing the effective mass is sufficient to capture most of the behavior for a wide range of relativistic mean field theory models. And so with these additional two parameters, we find that we're able to do a more rigorous treatment of the thermal pressure at the high densities. So this is now showing on the right side of this slide the non-cartoon version of the thermal pressure. So the diamonds represent the thermal pressure from one of these realistic, self-consistent equations of state at 3 different temperatures. The dashed lines show previously what was basically the state-of-the-art thermal approximation that was used and probably at least many of the neutron star merger simulations that are kind of in the literature right now. And then the solid line is what you can achieve by just using this parametrization of the effective mass. So our goal with this is that we can now keep the sort of convenient features of that simplification of the thermal pressure, where we can hope to do a large-scale parameter study where we can vary the cold physics a lot and have a more robust treatment of the thermal physics at high densities, and we can see what the effects are of varying these parameters in neutron star merger simulations. And we can directly play with the parameters of our effective mass model and see if those are perhaps measurable in post-merger gravitational waves, or the amount of matter that is ejected, or any of these late-stage observables. So just sort of to wrap up, all of the constraints that I showed are so far on the cold equation of state are all from this single event that was detected now 2 years ago. LIGO is now 5 months into a new 12-month observing run with upgraded detectors. In these first 5 months, they have detected 1 likely neutron star merger. They haven't published the details of it yet, but it seems likely to be confirmed. And there's potentially also a neutron star black hole merger that was just detected 2 weeks or so ago. Oh, it was just September 1st? Oh, I didn't see that one. Oh, okay. Okay, so maybe 2. but hopefully over the remaining year of this observing run, they will detect more and more of these. And as we start to build up statistical ensembles, we can start to shrink those error bars and hopefully get competitive constraints with other constraints that we have on the equation of state. And moving forward, I think as we start to want to be able to use these late stage observables to constrain the equation of state, we're going to need to start thinking more critically about how we're treating the thermal pressure. And then the other side of the issue that I didn't mention is that in the late stages of a neutron star merger, the dynamical timescales are so fast that the matter does not necessarily maintain its initial beta equilibrium composition. And so you can end up with slightly more proton-rich matter than you started with. And in most of these neutron star merger simulations that are using that sort of ideal fluid approximation, they completely neglect the effect of changing the composition. So the other side of the framework that we have that I didn't go into is another another set of parameters based on the nuclear symmetry energy that allows you to also explore what happens to your pressure profile when you change the composition at late stages in the merger. And so that's where our group is going with this, trying to do large-scale studies of these neutron star merger simulations to see what the role is of the effective mass particles, the strength of interactions, and the symmetry energy, and how we can use late-stage observables to ultimately get a new handle on those parameters. So I think that's where I'll stop for now, but thank you. Yes, this one?
Yeah. So you said that you did kind of relative calculations to get that model for what the effective mass should be. And I don't quite understand, I don't quite know the details about it, but it seems like it's a really complicated problem. I think it's a many level problem. So I was just kind of surprised that you have an analytic form of what.
This is a total parametrization. This is not derived in any sort of relativistic mean field theory sense. So I was just saying we are fitting results from mean field theory calculations with a simple parametrization.
So you sort of, how exactly do you know what you follow?
So we took the results of people who have calculated the effective mass for a variety of different equations of state, relativistic mean field theory equations of state. And then we fit the results from those. We didn't perform the calculations ourselves.
Can you give us some intuition for why the posterior on tilde lambda is bimodal?
That's a good question. Someone else asked me that this morning. I don't know. So I can't. I don't know if there's something fundamental there or if the data prefer it. You know, it's interesting. I gave you results on sort of one set of neutron star radius results. There are other teams that find neutron star radius closer to about 12.5 kilometers. So it's a little total coincidence, but you know, just kind of funny that sort of two teams measuring neutron star radii find 10 to 11 and 12.5 kilometers, and the gravitational waves also seem to point to that. I don't think there's anything fundamental there, but
within your parameterization, right, the bimodality here in this radius directly reflects the bimodality.
Yes, absolutely, right? This is just taking these results and hitting them with the Jacobian you calculate with our one-to-one mapping, with our lambda tilde of our function. Yes?
Would this resolve if there were a phase transition? Or would the distribution be totally different if you allow the phase transition?
So the two sets of X-ray radius constraints are from the same systems. So I think that bimodality just reflects some differences in the modeling, you know, some persistence in the modeling uncertainties that haven't yet been resolved. Different choices can give different answers. So I don't mean to suggest that there are actually two radii. I don't think the data are pointing towards that. For the single, you're saying just for the gravitational wave data, the two peaks. maybe. I don't know. I haven't thought very much about that. If the second peak could be a second. But this is, again, the binary parameter, not the tidal deformability of a single star. So I think if there was a phase transition, it would be washed out, and you could still expect just a single distribution in the answer. I'd have to think more about it. It's a good question.
So in the event one of these gravitational wave signals from the last observing run is a black hole neutron star merger, do you expect the uniqueness of that signal to help grant some insight into this problem?
So the nice thing about the problem, if it's a neutron star black hole, is that theoretically you expect the tidal deformability of a black hole to be 0. And so in that case, you don't have to deal with this binary tidal parameter. Instead, what is actually extracted is the clean tidal deformability of just the neutron star. And so in that sense, we don't have to worry about this, these new relationships I'm describing, because we can just directly infer, what the behavior of that tidal deformability of the single star is. But that's a good question.
Another question about final distribution.
Yes.
So the slope of the symmetry energy that you found from the model, you had this final distribution, and the peak was that one.
Yeah. This is jumping. Yes.
Yeah, it's around 20. But just eyeballing it, it seems to me this is not inconsistent with their experimental data. It seems that a value above 30 is just as likely as a value below 30, integrating that data because of the long tail.
30. Oh.
Right?
That's a good point. You're saying that the total area under this. Yeah. True. Yeah. And right, I mean, this is a very long tail that could still be consistent with values of 80, right? Right. But yeah, that's a good point. Thank you.
Can you explain what is the difference between gamma and
Yeah, so this is the power law that we're assuming for our equation of state, just between 1 and 3 times saturation. And we find that when you draw from realistic values for these coefficients, gamma of 3.5 is strongly preferred, but gamma of 3 and 4 are also still allowed, which is why we're showing them here. But it's pretty sharply peaked at gamma 3.5.
So 3 would be more or less.
Yeah.
To make a comment, the experimental one, experimental constraint of L0.
Yes.
Is, as you mentioned, that was extracted. Those are extracted at saturation density. That's why it was good. But actually, most of the data, I don't know about the ocean, but the Latina and Lim, most of the data for those things more sensitive to 0.1.
0.1 saturation?
I mean, no. 0.1.
Oh, 0.1, yes, okay, yes, 2/3 saturation.
So it's L0.
Yes, well, and my understanding too, right, it's not just an extrapolation in the density, but also in the temperature, because those are, right. So there are some uncertainties there, which perhaps is premature to say that, oh, the answer is 20. I don't think the answer is necessarily 20 either, but perhaps it might point. Yeah, they've always pointed to slightly lower values of L.
That's mainly coming from the light.
Light as in 1.4-ish, I think, right? Ed might know. I don't think so. We don't have any from like 2 solar mass neutron stars. But.
Well, seems like everybody has asked their questions, so let's thank again, Caroline.